All right, we can start now. Welcome back, everyone. Hope you had a really good week. Oh, someone just joined. Patrick. All right, almost a full class. Just missing one person. All right, welcome back, everyone. Hopefully you had a good week. Today we're going to look at a brand new topic. It's called combinatorics. But before we go into that, I had a few questions about one of the problems from last week's homework. So let me share this tab. So is this problem from the homework? It was part E, question 3, and this was from the 2018 9 chapters contest. It was the last problem on the part E as well. So I can read the question for you guys. So a message is a string of zeros and ones. Each digit is in a message is called a bit. And Rohan wishes to send Jasmine the 4-bit message 0101 across an unreliable communication channel. It's possible for some bits to be flipped from 0 to 1 or from 1 to 0. Each bit is flipped with a probability of 2/5. So that's the probability that a bit, like one of these bits, so like these zeros or ones, it's a possibility that they can be flipped to like the opposite one. So like flipped from 0 to 1 or from 1 to 0. So to make it more likely the message is delivered correctly, Rohan sends each bit of the message 3 times. So then the message he sends is 0001111 0201111. Right, Principal Joy. 金老师好。Okay, let's go back to the question. So Jasmine will try to decipher Rohan's message by looking at each 3-bit block. So like each 3 bits, like 000 and 111. And she would guess the original bit, so like from here. So the original like 4-bit message from here. So she would guess 0 if she sees a 000, a 001, or just like if there's only one bit of 1 inside these blocks of 3 bits. And she'll see the bit 1 if she sees these following bits right here. So here's an example. Jasmine could receive the message 101, 111, 001, or 101. And then these underlined bits, see if I can highlight, I can't really highlight that, but the underlined bits have been flipped from their original values. So we see from here, like say, look at the first block. So originally it was 000, and we see the first and last bit of that 000 were flipped to ones. That's what they mean. So Jasmine would look at the first 3 bits, and since she sees 101, so this one, she would guess 1 as the original bit because it's part of this rule right here. So she would guess a 1 as the bit Rohan intended to send, which is obviously incorrect. He intended to send 0. And so that means she would look at the message as 1101 instead of 0101, which is not correct. And the question asks, like, what is the probability that she'll guess the correct message exactly? And write the answer as like a fraction with powers, like that. And also, let's take the solution up on a canvas right here. Right, so let's write down the original bit. And also write down like the 3 digits as well. All right, so Rohan wants Jasmine to guess this message, right? 0101. And there are multiple ways in which, like, you can still have some bits flipped, and she'll still be able to guess this correct message. So we can see that the rules say that for 0, you can either have 000 or a 1 replaced with any of these. So like you have a 1 here, or like a 1 here, or a 1 here. But there can only be one, if you understand what I mean. And similar thing for the bit 1. You can either have 3 ones, actually, yeah, right here. Or you have 2 ones and 1 0. Hopefully it's not too confusing. So that means you can have like all 3 bits equal to 1, or you can have a 0 over here, or over here, or over here. But you can't have 2 or more zeros. Otherwise, it should see a message as a 0. So you can see here, so like from these 3 bits, you can the maximum number of bits you can change from each of these blocks is 1 in order to get the correct message. Because so say I choose 0, 0, 0, I can only switch one of the bits to 1, and that would because that would correspond to 0. And if I say change 2 or 3, that means the bit would correspond to 1, which is incorrect. So what we need to do is find the probability, write down right here. So probability that none of the bits are changed. So say no change. So the probability that none of the bits change, and remember that at most 1 bit can change. So we need to add that to the probability that exactly 1 bit changes out of the 3 blocks, like out of the block of 3 bits. So I just say 1 change. Right. Are there any questions about this so far? Especially for you, Bob. You understand this. Sounds good? Okay. Yeah, so we need to calculate this probability. Right. And this is only for 1 block. If we do it for all 4 blocks, we can just multiply them by each other. Yeah. So like take to the power of 4, I believe. That's what you can do. So let's get an expression for the probability that none of the bits change. So remember that the probability that a bit changes is 2 to the 5, right? Let me see. Yeah, okay. So probability that a bit changes, so let's write p change, or like pc, whatever. The probability that it changes is 2/5. And if the probability, if you've learned probability before, like probability of like the opposite outcome. So like if there's no change, let's write NC. So probability of the opposite outcome will just be 1 subtract the original outcome. So 1 subtract PC. So 1 minus 2/5. And that simplifies to 3/5. So probability that 1 bit doesn't change is 3/5. Now we need to calculate the probability that all 3 bits don't change. And the way you do that, you just take the cube function to that. So because there's 3 bits, you're multiplying 3/5 by itself 3 times. So that means you can just take to the exponent 3. So probability that none of the bits change for 1 block is 3/5 cubed. And we'll simplify that later. Right? And now probability that 1 of the bits change. So remember that a bit can change with probability 2/5, right? So that means we will need that fraction in there. So this is a probability that 1 bit changes. And we also need to make sure that the other bits don't change as well. Remember that they don't change with probability of 3/5. So the other 2 bits that don't change, they have probability of 3/5 squared instead of cubed, because now it's 2 bits, not 3 bits. And the 2/5 represents the bit that did change. But what we need to do here is I remember that the first bit, the second bit, or the third bit can change, right? So we need to multiply this number by 3, because you can have the bit like change a bit in a different place. And I think this is pretty similar to what we're going to learn today about combinatorics. So I'll get to that later in a sec. And here I'm not sure to calculate this. Let me look at the solution. Yeah, what you should get here is 81 over 125. Yeah, it is from the solution page. I had to look at it. Didn't want to calculate myself. Or you can just write this as a power. So like this is 3 to the 4, and then the denominator is 5 to 5 cubed. All right, so this is the probability that one of the blocks will be guessed correctly, okay? So it's 3 over 4, 3 to the 4 divided by 5 to the 3. And now to get probability that all 4 bits, so all 4 of these blocks are guessed correctly, we just take the exponent 4 for this expression. So, right, like this. And take that to the exponent 4. And if you know your exponent rules, you can just multiply the exponents together. So you multiply the 4 with 4, you can multiply the 3 with 4. And what you're left with is 3 to the 16 over 5 to the 12. And that's the format we wanted. Like the question wants the answer in. So this is the perfect format. So that's final answer. So it's 3 to the 16 over 5 to the 12. Are there any questions about this? Yeah, Bob, did you understand this now? Oh, like from here to here? Like you want to know how I calculate that? I just looked up the solution. I was a bit too lazy to actually do it myself, but I can try it out right now if I want to. Um, let's just do it right here. So I have 3 cubed over 5 cubed plus. So now for the for numerator you have 2 times 3 squared times another 3, so times 3 cubed. So like this. And you just combine these together. And just make one 5 cubed, right? And if you calculate the top, so like 27 plus 2 times 27, so 27 plus 54. Well, that gives 81. And 5 cubed is 125. Right, so there, that's how I calculate it. Is that clear, Bob? Right, sounds good. Okay, okay, I took longer than expected on that question. But did everyone understand the solution? Yeah, this was So this was from the 2018 nine chapters contest, and it was the last question on part E. So pretty difficult. And if you're in grade 7, 8, that was like this will be like the last problem you solve on the entire contest. So yeah, it definitely have to be pretty difficult. But let's get to today's lesson. So today we're going to learn about something called combinatorics, and let's learn what combinatorics actually means. So combinatorics simply is just the math of counting and arranging. So for example, trying to find the total number of arrangements of a line of people. So like people lining up in front of something. Find the total number of arrangements, like how many arrangements you can have for a person, like people to be placed. And combinatorics uses math. Oops, didn't mean to click. And so combinatorics uses math to count quantities that are too large to be counted by hand. So, for example, if you want to say like a line of like 200 people, like how many arrangements are there? You can't. If you try to like count that by hand, that would take like way too long. So you need to use like formulas and math to just solve for that. And we'll see how to solve those kind of questions later on. So first, let's learn a few rules. So the first rule we're going to learn is called the rule of product. So this states that if there are m ways to do something, m is a variable. If there are m ways to do something, and then n ways to do something else afterwards, then the total number of ways to do both actions is m times n. And I'll give an example just to make that more clear. So for an example would be like flipping a coin twice. So for the first flip, you can have two outcomes, right? You can have heads or tails. So now if you flip it twice, to flip it a second time, so that second flip comes right after the first flip. So that means you can do the rule of product. And for a second flip, it's also two outcomes, heads or tails, right? And if you want to count like the total number of combined outcomes for the two flips, so you can actually count that. You have like heads, 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 tails, or like tails, heads, tails, tails. But then mathematically, that would just be 2 times 2. So outcomes from the first flip times the outcomes from the second flip. So 2 times 2, that gives you 4 outcomes for both flips. That's the rule of product. Right, now let's look at the rule of sum. So this states that if there are m outcomes of an action and n outcomes of something completely independent from that action, then the total number of ways to choose one of these outcomes is m plus n. So that's rule of sum. And then here's another example. Here's an example for the rule of sum. So you're choosing routes to go from Waterloo to Toronto. And I just made these statistics up. Say there are like 2 highways that get you from Waterloo to Toronto, and also that 3 railways that you can take. So then the total number of routes you can take would be, you just add these numbers together. So 2 plus 3, and it gives you 5. So 5 total routes from Waterloo to Toronto, but just by using the rule of sum. Right? Are there any questions? No questions? Right? Hopefully that was clear. Let's try a problem with the rule of sum product. So Eric, currently in downtown Vancouver, wants to make his way to a skiing hill in Whistler, which is owned by a ski resort. So he can either drive to the ski resort or take 2 different train routes to a station nearby and walk there. And then from the ski resort, he can take 3 different ski lifts to the hill. So how many routes can Eric take to get to the hill? Grammar error, forgot to put an S there. So the question asks for how many routes can Eric take to get to the ski hill. Give you guys a few minutes to look at it. I'll wait a couple more seconds. Does anyone have an answer so far? Just curious. Not yet? Yeah, this is math. Oh, yeah, Elaine. You said 9? It is 9. I'll take up the solution right now. So the answer is 9, but let's see how we got that. Okay, so for just for better understanding, I'm gonna draw a diagram. So let's say this point is Vancouver, and then this is the ski resort. It's called R, and this is the ski hill called H, right? And so from here, we can try drawing the routes that take you from Vancouver to the resort and then the resort to the hill. So remember, one way that he can, so that Eric can go to the resort is just simply driving there. So let's say this is the route where he drives. It doesn't matter. But like, so say that's the route that where he drives. And then it also says he can take 2 different train routes there. So that means we can add two more paths from V to R, right? So just like that. So you see here, we can just use the rule of sum to figure out like how many routes there are from Vancouver to the resort. And so that's just 2 plus 1, right? Which is equal to 3. So then you have 3 routes from Vancouver to the resort. You either walk there or 2 train routes. Sorry, drive there or 2 train routes. And the next part of the question, to get from the resort to the the ski hill, you can take 3 different ski lifts. So we can just draw the same thing. So 1, 2, and 3. So here we have 3 different routes from R to H. We also have 3 different routes from B to R. And so now what do we do with these numbers? Can someone tell me? So what do we do with 3 and 3? We multiply them. Yeah. So we use the rule of product now. Because so like this action from R to H, it happens after from like the route from V to R. So that means we can just take the product of both these outcomes to get the total number of combined outcomes. So it means 3 times 3, which would give you 9. And if you want to like double check that, you can try like drawing out the routes, like the possible routes yourself. So say I took this top route from, this top route from B to R. So I'd say it took that. And then from here, I can take 3 routes to R to H. And the same thing for the other routes from V to R. So each of these has 3 routes that they can take from R to H. And then so that's why you multiply the 3's together. Are there any questions about this? No questions? But yeah, that was a pretty simple question. Let's go back to the slideshow. Right. So this is a problem. Here's the next slide. You're gonna learn 2 new terms, or this might be a review if you guys did Olympic math with me last year. But so we're gonna learn permutations and combinations. So let's look at the first term. So what are permutations? First of all, permutations are arrangements where the order matters. And here's an example: 4-digit pins on your phone. So say my 4-digit pin was 1234, which it isn't, of course. Otherwise, that'd be stupid. Like, say it was 1234. This is a different pin from 1324, right? Like, these 2 pins are completely different. If I enter 1324 on my phone, which activates with 1234, then it wouldn't activate, right? So these are what permutations are. And let's look at the next term, combinations. So combinations are arrangements where the order does not matter at all. So like basically the complete opposite of permutations. For example, say you're choosing 3 teachers to write reference letters. And then so the order in which you pick the teachers doesn't matter because they're just all going to write a reference letter to you in the end anyways. So that's what a combination is. Are there any questions? That's a permutation, yes. That wouldn't work, no. Like, oh wait, oh you're saying if the pin was a combination and if you type 3214 instead of like 1234, then that would work. But like in our world, it obviously doesn't work. So yeah. Yeah, exactly. Yeah. Yeah, that's what a combination is. Doesn't matter like the order which you pick the outfit. Like say you pick the hat first, or where you put on the sweater first. Doesn't matter. I'm not sure if I would call that a permutation, but yeah, that works too. A leaderboard. Yes, yes, yes. Yeah, that's a good analogy. Yeah. So the order matters for permutations. Order does not matter for combinations. Right? Any other questions before I move on? Okay, sounds good. Let's look at this might be reviewed to some of you. Let's look at a factorial. So let's say the variable n is a natural number. So n has to be a natural number. It can't be like a negative number or a zero or a decimal number. So say n is a natural number, so from 1 to infinity. And so n factorial, we write factorial with an exclamation mark. So n factorial would just be the product of like all of the integers that are smaller or equal to that number. So you go from n times n minus 1 times n minus 2 all the way to 3 times 2 times 1. And we use factorials very, very often in combinatorics problems. So here's an example. Say you're arranging 4 people in a line. And this is a permutation because the order of the people in the line matters. So total number of arrangements here is equal to 4 factorial. So that's 4 times 3 times 2 times 1. And this is equal to 24. I'll try to explain why that works too. Let me go back to the whiteboard. So you're arranging 4 people in a line, right? And we know that's a permutation where the order matters. So say I have these 4 spots. So I want to pick people and place them in a spot. So let's choose the first spot right here. So how many ways can I put a person in this spot right here? Say this was a first person line. 4. Yeah, exactly. Yeah. No, you don't have to divide by anything. Yeah. Okay, well you see here, the number of combinations is actually 1 right here. Because now the order doesn't matter where you place them. As long as they're all in that line. That's 1 combination. Yeah. So there'll only be 1 combination if this was a combination, but we're looking at permutations, right? The order matters. So what I'm trying to explain here is that for each of these spots, you're trying to figure out like how many people can you place in that spot. So say the first spot, you can place 4 people. Let me draw like, I don't know, some circles just to represent people. So after you place that first person, let's say this person right here is gone. So like he's already in the spot. And now the next spot, so the second person in line, now you can only choose from 3 people because the fourth this person was already chosen. So that means for the second spot, you can choose 3 people, and then the number continually decreases by 1 as you move on. So 4 times 3 times 2 times 1, and this is equal to 4 factorial. You notice that, and that's equal to 24. So that's why you can use factorial to solve these kind of problems. Right? Are there any questions? No questions? No, it's just an exclamation mark. Nothing fancy. Yeah. Oh. Right, let's move on. A problem. Okay. So the generic names, Alice, Bob, Carl, David, and Earl, which I use in all of my problems, are lining up to register for the upcoming 9 chapters on the mathematical art contest, which isn't happening this year, sadly. How many possible arrangements are there if Alice must be the first person in line? And are these arrangements, permutations, or combinations? So let's answer the second part of the question first. So are these permutations or combinations? Someone just shout it out. It's a permutation, but like the way you explained that wasn't very clear. So like the order of the people matters, right? Like in which they try to sign up for the contest. The order in which they're placed in the line matters. So that's why it's a permutation. Yeah, he knows. Yeah, that's the trick. He ignored Alice. But No, it matters. Yeah, okay. The person one. Yeah, it matters. Yeah, assume these are permutations. Wait a few seconds before I take it out. Okay. I think I'll take this up now. It is 24. Okay, so let's use that analogy where we just draw like the number of spaces to represent like each person in the line. That's very helpful. And so Devin knows the cool trick, right? So the question asks for like how many arrangements there are if Alice is the first person in line. So that means the first person in line can only be one person. It's Alice. I'll just write A right here. Say this was the first spot in line. So I mean here, this means that for the first spot in line, there can only be one possible outcome, right? It's only Alice. And now for the next few spots, so we have 4 spots left, and then 4 people left to choose from, right? So it means for the second spot, we have 4 people, and this spot we have 3 people, and then here we have 2, and then here we have 1. And so you notice that this is 4 factorial, which is equal to 24. And so that's the answer for this question. Are there any questions about this? Yeah, I mean, yeah, this rule product does apply here. Mhm. Any other questions? Nope. Sounds good. Okay, let's look at some notation, some choose notation. Right. So say I had to choose k objects out of n objects, and so the total number of combinations. So these are we're assuming that these are combinations. The total number of combinations I can choose for these k objects would be n choose k. So like you have in brackets on the top you have your total number of objects, and then on the bottom, so kind of like a fraction, except where you don't have that divide line. On the bottom you have the number of objects that you have to choose. So this is called n choose k, and this is equal to this fraction right here. And I'll decompress each of these parts. So in the numerator we have n factorial. So remember, exclamation mark is just factorial, and then that divided by the denominator. In the denominator, we have a few terms. First, we have k factorial, right? And then that is multiplied by, in brackets, n minus k factorial. And here you have to do the n minus k first before doing the factorial. You can't just do like n factorial minus k factorial. That doesn't work. You have to do first do the n minus k operation first before you take the factorial of that. Any questions about this notation? No questions? Right. Let's look at a problem with choose notation. So Mr. Trump is a very strict and odd teacher. Every day after class, he picks 2 random students from his class of 20 students to clean the whiteboard for him, as he likes watching his students suffer. How many ways are there for Mr. Trump to choose those 2 students? I'll give you guys a minute or so to solve this. 190. I think that's correct. Wait a few extra seconds. Okay, let's take this up. So over here, we're choosing 2 students out of 20 students. So that means we can use this choose notation, right? So we're choosing k objects out of n objects. So it means here k would be 2 and n would be 20. So we can just substitute those values into the notation. And so let's try it out. Let's get a new whiteboard, new drawing. Okay. So we have n is equal to 20 and k equal to 2. Right? And we can substitute this directly into the n choose k notation. So we had n on the top, so we 20, and then we had k on the bottom, so 2. So this is 20 choose 2. That's how we would say this expression. And so if we try to solve this, like substitute it into the fraction, we would have this 20 factorial on the top. On bottom we have k factorial, which is 2 factorial. Yeah, so 20 factorial is n factorial. 2 factorial is k factorial. And we have n minus k factorial. So 20 minus 2 factorial, just like that. All right, we can, let's first simplify this out. So we have 2 factorial times 18 factorial on the bottom. And on top, we have 20 factorial. And you might be thinking that we have to like calculate like these large values right here. So we have to do the 20 times 19 times 8 times blah, blah, blah. But we don't have to. So the way we simplify this is we just look at any common terms within these factorials and we cancel them out. So I'll show you guys. So remember, 20 factorial is 20 times 19 times 18 times blah, 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 all the way to 1. All right, times 2 times 1. Okay. So we have 2 factorial as well. We have 2 times 1. 18 factorial is just 18 times 17 times blah, blah, all the way to 1. Yeah. All right. So we expanded each of these factorial values. And you can notice that we can cancel out some of these terms because this is a fraction. We can cancel out some terms from the denominator with terms from the numerator. So you can see here that 18 and 18 would cancel. There'd be a 17 over here, so that this 17 would cancel. And you'd notice that like everything in between these numbers would also cancel. And same thing with the 2 and the 1. So we don't need to look at those values anymore. So we don't need to calculate that large product or anything. We just simplify these values. And so what we're left with is 20 times 19 over 2 times 1. Okay, so because like all the numbers from 18 and below got canceled out, we're just left with these 2 terms on both the denominator and numerator. And we can also simplify this. So we can cancel out cross multiply the 2 with the 20. 20 will become a 10. So this is 10 times 19. And that's our final answer. If we simplify it, we get 190. Right? So we have 190 total combinations for this. Are there any questions? No questions? All right, sounds good. I think the remaining part of the slideshow is just a bunch of problems. Just 3 more problems. Okay, so here's problem number 1. Devin is stuck picking an outfit to wear today. In his closet, he has 10 t-shirts, 6 pairs of pants, and 5 pairs of socks. How many different outfit combinations can he choose, such that he needs to wear 2 t-shirts, because he's an odd boy, 1 pair of pants, and 1 pair of socks? And let me specify something, actually. Assume that the 2 t-shirts that he picks, assume that those are combinations and permutations. I know, like, you can like wear one inside and one outside, but let's just assume they're combinations for now. Give you guys like a minute or so to look at this. I will take this up now. Right, back to the whiteboard. Okay, so his closet has 10 t-shirts, 6 pairs of pants, and 5 pairs of socks. If you want like a diagram, we could just express like each of these closing items with dots. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have 6 pairs of pants, 5 pairs of socks. And so from here, you can just draw lines from each of these dots to the next, just to show like that outfit combination. But here, there's a lot of lines we'd have to draw, so I'm not going to do that. But here, you can understand like how the outfits would work. So I'll write the numbers here as well. So 10, 6, and 5. So here, Devin wants to choose 2 t-shirts, one pair of pants, and 1 pair of socks. So you'd think we'd have to we just multiply 10 times 6 times 5 and call it a day. But not necessarily, because Devin has to choose 2 t-shirts instead of just 1 t-shirt. If it was just 1 t-shirt, 1 pair of pants, and 1 pair of socks, you can just multiply 10 times 6 times 5 because product of the rule of product. But, so since he's choosing 2 t-shirts out of 10 t-shirts, we would have to express that as choose notation. So you're choosing 2 things out of 10 things. So that means we have to write this as 10 choose 2. Oops, didn't mean to put a fraction. And from here, we can just multiply 6 and 5. But we can also express these, so we can express the pairs of pants and the pairs of socks as well with choose notation. And the way you do that would be just 10 choose 2 times 6 choose 1 times 5 choose 1. But what you would realize is that this is just equal to 6, and then this would be equal to 5. So like n choose 1 would just be equal to n. And we can prove that, but you guys should understand why that is. So here you can only have 6 ways to choose pair of pants and 5 ways to choose pair of socks. Now we need to figure out what 10 choose 2 is. So let's write it down right here. Write the expanded expression as well. And this is 10 minus 2, which gives you 8 factorial. Does anyone know what this is equal to? 45, yeah. So like 10 factorial kind of has an 8 factorial inside it, so that means this would just become 9 times 10. And you're just left with 2 times 1 here. And 9 times 10 gives you 90, divided by 2 gives you 45. So that's 10, choose 2. So 45 times 6 times 5. And see what that's equal to. I think that's 1,350. Can someone double check that for me? If this is right. Okay, sounds good. Okay, this is the final answer for the question. And if you were to assume that the two t-shirts are permutations, just because you're thinking of like if he wears like one t-shirt inside or the one t-shirt outside and it's considered like different outfit, then all you have to do is multiply this value by 2. Just because that for each of those like t-shirt combinations, you can switch them around. And so there are like 2 different arrangements for that one combination of t-shirts. So you multiply that by 2. And that would leave you with like 2,700. Yeah. Any questions? No questions? All right, let's go on to problem 2. In a game of blackjack, I choose 2 cards from a deck of 52 cards, while my opponent chooses 1 card. And just assume that I choose first. How many possible combinations of cards can there be if our personal decks are considered individually? So what I mean by that last statement is that like, say I choose say if we combine our uh, cards together, and it would be like the same combination as something else. Actually, never mind. I'm not sure how to explain this. It's confusing, but I'll show on the whiteboard actually. So what I mean by that last statement. Okay. So here's my deck, and here's the opponent's deck. Say I chose like an ace. Say these were like heart cards. So ace of hearts, and like 2 parts. And then my opponent chose like 3 parts. And say instead that I had an ace and a 3, and my opponent had a 2 parts. These are considered different arrangements. Right here. These are different from each other. So that's what I meant by the last statement. Right here. Give you guys a minute to think about it. Think about how we could solve this. And assume that I choose before my opponent. I choose my 2 cards before my opponent chooses their card. Okay, I'm gonna take this up now. Alrighty. So the deck of 52 cards. First, I get to choose 2 of them. So I'm choosing 2 cards out of 52 cards. So that means we can use choose notation to express that. So here we would have 52, choose 2. Right? And now our opponent, after I choose my 2 cards, my opponent has to choose 1 card. But then how do we express that as choose notation? Can someone tell me? So we're choosing 1 card out of how many cards? Not 52. Yeah, think carefully. 50, yes. So I said that I choose my 2 cards first before my opponent. Oh, we assume that. I forgot to mention that in the question, but I just decided just assume that. So after I chose my 2 cards, that means that there are 50 cards left in the pile because 52 subtract 2 gives you 50. And so it means my opponent would have to choose 1 card out of 50 cards. So that means you would have 50 choose 1 for my opponent, and 52 choose 2 for myself. And then what you would do with these 2 values, you would just multiply them, because the rule of product states that like if you have m outcomes of an action and then n outcomes of an action that happens right after that, so my opponent's choosing cards right after I choose my cards. That means we can use a rule of product, just multiply these values together. And let's try to solve for 52 choose 2. So 50 choose 1 is just 50. So anything choose 1 is just itself. Just keep that in mind. Now 52 choose 2. So you'd have on the top 52 factorial. Bottom you have 2 factorial times 52 minus 2 would give you 50. 50 factorial. Just like that. Right. So the 50 factorial would cancel out with, so inside the product of 52 factorial, it will cancel out all numbers from 50 and beyond, so lower than 50. So that means here you're left with 52 times 51. And then on the bottom, you're left with 2 times 1. And so you can simplify this. You can cancel out the 2 and 52. You get 26 times 51. Right. I'm too lazy to calculate what that is, so I'm just going to write it down right here. Right, so 52 choose 2 is 26 times 51, and then 50 choose 1 is just 50. So 26 times 51 times 50. So that would be your final answer. Does anyone know what this is equal to? Like if you typed it in the calculator. So 66,300. I don't can't really do it on my head. Let me try to find a calculator. I mean, if it works for your calculator, it should work for mine too. Yeah, that's correct. That's your final answer. Are there any questions about this? Yeah, so final answer is like not really that important. All you need to know is like how you got that answer and like the product of the numbers that come with it. And I think there's one final problem after this. Yeah, it's final problem. Okay, if you can only go up and right from start to finish, how many possible paths are there? Give you guys a minute to look at this. And try to solve it with combinatorics as well. I know you could probably solve it with some other method, but try to use combinatorics for this. Okay, I think I'm gonna take this up now. Get a new drawing. So if you notice in the maze, I think it was a 5x3. Yeah, 5x3. 1, 2. Yeah, 5x3. Well, not a maze, but it was a grid. So it's 5 by 3. Right? And we're trying to go from the bottom left corner to the top right corner. And so let's try drawing out like a sample path. So let's say 1, 2, 4, 5, 6. Look like that. Say I just took the path that ran along like the perimeter of the grid. So like that. 1, 2, 3, 4, 5, 6, 7, 8. And you're gonna see why I'm counting these. So remember I counted 8 of these lines right here. So 1, 2, 3, 4, 5, 6, 7, 8. Oops, watch ran out of battery. Okay, and so you might be wondering like how this is related to combinatorics. But say I chose another path instead. So say I went, so from this point, I go up 1, 2, 3, and then right there. And you notice that there are also 8 lines that you have to draw to get from here to here. And this is true for any path that you take along this grid. And assuming that you can only go up and right. So there are a total of 8 like possible how do you describe it? It's like edges that you can take. 8 edges that you need to pass in order to get from bottom left corner to top right corner. Okay, that makes more sense. And so with these 8 possible edges, so let's draw out some spaces right here. And for each of these spaces, what we can put inside is the direction that we can go. So say for this one, we choose to go right. So we go right here, over here as well, over here as well, over here as well. And then for the last 3, we just go up to get to our destination. Right? And what you will notice that for any path, that you have to go right 5 times and up 3 times as well. So say you chose the path that went from here to here. So this one as well. You can see that there are 4 rights over here, 3 paths going up, and 1 time going right as well. So 5 times going right, and 3 times going up as well. And so the way you want to solve this problem is that you're trying to figure out like how many possible combinations, how many different like permutations, permutations of like of these there are. So permutations. And we can actually use choose notation to express this. I know choose notation is for combinations, but so here we're going to use permutation. We're going to still use choose notation here. And the way we do that, so from 8 spaces, say you want to pick, so from out of each of these 8 spaces, we want to pick 3 of them for our up directions, or say you want to pick 5 of them for our right directions. Okay? And so we express this as choose notation would be 8 choose 3, or you could do 8 choose 5. And what you realize is that both of these are actually equal to each other. And if you try to solve for that, you would get 8 factorial over 3 factorial times 8 minus 3, which is 5 factorial. And I'll show you why these are equal to each other as well. So this one would be 8 factorial